The last period we have studied about few rules for filling up of the electrons. The first rule that we have studied was about the Pauli's Aufbau rule. This Aufbau rule tells us about the energy of the orbitals, and according to this rule, Aufbau rule, in the ground state of the atom, the orbitals are filled in the order of their increasing energy, and we can here understand the order of increasing energy is 1s, then 2s, 2p, then we have 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6x, 4f, 5d, 6p, 7s, 5f, 6d, 7p, and 8s. So this is how we can understand about the filling up of orbitals in the increasing order. So you can see here, this is even a way by which you can remember this order. Then we have studied about the Pauli's exclusion principles, and this principle says that no two electrons in an atom can have the same set of all four quantum numbers, or we can even say about it as only two electrons may exist in the same orbital, and these electrons must have opposite spin. Then we have studied few examples, and we have understood that even if two electrons are filled into the same orbital, they may have their principal quantum number, azimuthal quantum number, and magnetic momentum quantum number same. But as they are filled with the opposite spin, their spin quantum number would not be same, and that is how at the same time all four quantum numbers for any two electrons can never be same. So this is how we understand about the Pauli's exclusion principle, and we need to study now about the Hund's rule of maximum multiplicity. This rule is for the degenerate orbitals. That means the orbitals which are having the same energy. So like px, py, pz, for example, px, py, pz, or dxy, dyz, dzx, dz square minus y square, and dz square. This rule says that pairing takes place into the orbital in a particular conditions. So pairing of electrons in the orbital belonging to same subshell does not take place until each orbital belonging to the same subshell is singly occupied. Same way, my dear students, we can say the same rule in another words, that pairing of electron in the orbital belonging to the same subshell does not take place until each orbital belonging to the same subshell has got one electron each. So this is how, my dear students, we can easily understand about the pairing of electron. Now this is what, if we understand it with the examples, we will understand it better. And let us start studying about the electronic configuration. If you are asked, define what is electronic configuration, so we can write the definition as the distribution of electron into the orbital of an atom is called electronic configuration. So when we know about the atomic number of an element, and so the same number of electrons are present into that particular element in its ground state or in its neutral state. So this number of electrons are arranged into the increasing order of their energy of their orbitals, and this is how the lower energy orbitals are first filled, and then the electron goes to the higher energy orbital. But suppose the electrons are going into the same subshell, and they have the degenerate orbitals like px, py, pz, and dx y, dyz, dzx, dx square minus y square, and dz square. Then the electrons are filled into the all five orbitals first singly, and then there will be pairing starts. So let us understand electronic configuration as well as all these rules one by one. So now we will start studying about the electronic configuration. We will start with the first element, hydrogen. The atomic number is Z. The lowest orbital is 1s. So in 1s, one electron is filled. So for hydrogen, we can write 1s1. We can even represent the electron into the box type of orbital, and we will represent the orbital in the form of box. So you can see that in the 1s orbital, I have filled one electron. Same way, if you go to the helium, that is the atomic number 2, we can write 1s2. And then, you know, the same orbital, there is no degenerate other orbitals available. So the pairing takes place in the same 1s. Electrons are filled in such a way that at least ms remains different. So here you can see that in the same orbital, two electrons are filled. One electron is filled with the up spin, another is filled with the down spin, and that is why their spin quantum number remains different. Now we will move and study about the other elements. Then we can move to the Z number 3, which is lithium. Lithium has 3 electrons. So first 2 electron goes into 1s2, and then the another electron goes to the 2s orbital. So according to the Aufbau principle, you know, 1s, after 1s is completely filled, the electron goes to the 2s orbital. To shorten the electronic configuration, instead of 1s2, we will write, or for convenience, we will write helium. So we can write lithium is the the electronic configuration of lithium is equal to helium into, after that, 2s1. So we represent the electronic configuration as inert gas and then the outer orbitals of that inner gas. The electronic configuration of the inert gas is known as the core electronic configuration, and this outer orbital electronic configuration is known as the valence shell electron. So this is how we can understand the electronic configuration in the form of the core electronic configuration as well as the valence electronic configuration. Now we'll move to the Z is equal to 4, which is a beryllium, and beryllium goes helium 2s2. You can see that the in 2s, the next electron is filled with the opposite spin. Now it goes to the boron, atomic number 5, helium 2s2, 2p1. So the first electron goes to the 2p and it is singly occupied. The second electron in the carbon Z is equal to 6, helium 2s2, 2p2. So these two electrons are filled in both the orbital with the same spin, my dear students. There is no pairing takes place. All the electrons are filled with the same spin. Now we cannot write 2p2 as it is shown under the bracket or under the box, which is a green, which is covered with a green line, and we cannot fill both the electron by making pairing into the first orbital, because these orbital of 2p are like 2px, 2py, 2pz. They are degenerate orbitals, and pairing starts only when all the three orbitals are singly occupied, or all the three orbitals have one electron each in them. And that is why in the nitrogen Z is equal to 7, helium 2s2, 2p3, we fill all the electrons in with the same spin, and all the three orbitals are filled with the electron which is single electron, and they all three electrons have the same spin. So next, if we take the atomic number 8, that is oxygen, we can write the electronic configuration as helium 2s2, 2p4. And now the fourth electron goes into the first orbital where the pairing starts, because all the three orbitals, which are the degenerate orbitals, and they have been filled, uh, or they have been occupied singly, or has got one electron each. So now the pairing start according to the Ohm's rule. In the same way, if we have the atomic number 9, then we have fluorine. The electronic configuration is helium 2s2, 2p5. And then you can see that in the 2p orbital, the pairing took place. And then we have the neon atomic number Z is equal to 10. It is helium 2s2, 2p6. So again, the 6 electrons are filled, and you can see that all the 2s and 2p are completely filled, and that is why we consider it as a neon. In neon, you can see that all the orbitals like 1s, 2s, and 2p, they are completely filled, and that is why it is known as the inert gas. And for writing the electronic configuration of the other element having atomic number higher than neon, we will write neon as a core electronic configuration, because it is completely filled. So when you have sodium Z is equal to 11, you write it neon 3s1, and one electron is filled with the up spin. Magnesium Z is equal to 10. It is neon. Neon means 10 electron. That is 1s2, 2s2, 2p6. So magnesium neon 3s2. The in the s orbital, the electron is filled with the opposite spin. Then we have Z is equal to 13. Aluminium. Aluminium has got neon 3s2, 3p1. So in the p orbital, one electron goes with the same spin. When atomic number is 14, we have silicon, it is neon 3s2, 3p2. So in the p orbital, 2 electrons are filled with the same spin. In the phosphorus, we have neon 3s2, 3p3. So all the three px, py, pz are filled with the same upside spin. Then we have sulfur, atomic number 16, neon 3s2, 3p4. Again, 4 electrons are filled with the one orbital paired inside it, and then chlorine Z is equal to 17, neon 3s2, 3p5. So when the 5 electrons are filled, the 2 orbitals are being paired, and then at last we have argon, which is having the atomic number 18, which has neon 3s2, 3p6. So all the orbitals present into the valence shell have been completely filled, and that is why argon is again an inert gas, and it has got completely filled electronic configuration. So for the other element, we will use argon as a core electronic configuration. So when you have atomic number 19, you have potassium. Potassium has got the electronic configuration like argon 4s1. This argon is nothing but your 1s2, 2s2, 2p6, 3s2, 3p6, and this argon represents 1s2, 2s2, 2p6, 3s2, 3p6, and then you have the 4s1. So I have shown you that in 4s orbital, one electron is filled with the up spin. Then you have calcium, Z is equal to 20, which is argon 4s2. So the another electron goes pairing into the 4s orbital. Then we have the scanium. The scanium has got the atomic number 21. The electronic configuration for scanium is argon 4s2, 3d1. My dear students, please remember that the energy of 3d is more than the 4s, because n plus L value of 3d is more than 4s. So we know the order that 1s, 2s, 2p, 3s, 3p, 4s, 3d. So after 4s, we'll have to fill 3d, and that is why here the electron goes into the 3d orbital, which is inside the 4s. So this 3d orbital is more near to the nucleus as compared to the 4s orbital, or the distance of 3d orbital is distance of 3d orbital from the nucleus is less than the distance of 4s orbital from the nucleus. Now again, Z is equal to 22. We have titanium, argon, 4s2, 3d2. So now the second electron goes into the another degenerate orbital with the same up spin. It does not get paired into the first orbital with the down spin. So these are the degenerate orbitals, and all these degenerate orbitals have to be singly occupied, or must have one electron each, and then we can start pairing. So in the vanadium, Z is equal to 23, argon 4s2, 3d3. In the chromium, Z is equal to 24, argon 4s1, 3d5. Now this is an interesting case, my dear students, where you can easily understand that chromium should have 3d4, 4s2. So it should have the electronic configuration 4s2, 3d4, but it is not. As the completely half-filled electronic configuration is considered to be more stable, to stabilize more, one electron from 4s goes to the 3d orbital, and then in chromium, the electronic configuration is considered as 4s1, 3d5. So even in chromium, we have 3d5 electronic configuration. In manganese also, we have 3d5 electronic configuration, because this 3d5 electronic configuration is considered to be more stable electronic configuration, and this is how we study about the stability of electronic configuration. When we have manganese, manganese is Z is equal to 25. So argon 3D, 4s2, 3d5, where all the 5 orbitals of 3d are singly occupied, and 4s has got pairing. Here you can, chromium, you can see that there is not even a pairing in 4s orbital, and 4s has got only one orbital. So total 6 unpaired electron you can see in chromium, whereas in manganese you can have the 5 unpaired electron. Then we have iron. Iron has got atomic number 26, so it is argon 4s2, 3d6. You can see that the pairing starts into the 3d orbital, and the first orbital is being paired. Then we have cobalt, atomic number 27, which is argon 4s2, 3d7. So the second orbital of the D has also been paired. Nickel, zinc, atomic number 28, argon forest 238. So again the third orbital of the D, again the third degenerate orbital of D has been paired. But now it comes to the copper. Copper again has a special case. That is why I have made a red star against it. It is the electronic configuration argon forest 1 3d10. As this is 3d10, which is the completely filled electronic configuration, to stabilize it, the electron from forest come to 3D and 3D become 10. This 3D10 is very stable, and that is why the electronic configuration of copper is an exception, and this is how we understand about the stability of completely filled and completely half filled electronic configuration. Please remember the electronic configuration of copper, Z is equal to 29 is argon forest 1 3D10. And then we have zinc, that is Z is equal to 30, which is argon forest 2 3D10. Then we have, my dear students, gallium, atomic number 31. Here 3D has been completely filled, so next 4p is there, and the electron goes to the 4p orbital. So gallium Z is equal to 33, argon forest 2 3D10 4p1. Gallium atomic number 32, argon forest 2 3D10 4p2. No pairing takes place and the electron is filled with the in the p orbital of the degenerate orbital with the same up spin. Then we have uh, arsenic, where we have argon forest 2 3d10 4p3. All the three electrons are filled with the same spin, and then the pairing starts. That selenium Z is equal to 34, argon forest 2 3d10 4p4. So the first orbital being paired. Bromine Z is equal to 35, argon forest 2 3d10 4p5. Again you can see that in the 4p orbital, second orbital has been, or 4p second orbital has been paired, and you can see into chromium, krypton, atomic number 36, all the orbitals have been completely filled, and it is argon forest 2 3d10 4p6, and that is why krypton is again an inert gas. And for writing the other electronic configuration, krypton would be considered as a core electronic configuration. So this is how, my dear students, you can write the electronic configuration for the other elements too. Here we see chromium and copper violating the Aufbau principle. This is what it is observed because fully filled orbitals and half filled orbitals have extra stability. That means if you have the electronic configuration like P3, D6, D5, D10, F7 and F14 causes this will be more stable always as compared to the other electronic configuration. Now we need to understand the various causes of stability of the completely filled and half filled subshell. So what are the reasons? Completely filled and completely half filled subshells are stable due to the following reason. The first reason is symmetrical distribution of electrons. So symmetry leads to stability. Completely filled or completely half filled subshell have symmetrical distribution of electron in them, and that is why they are more stable. Then we have the another, my dear students, please try to remember that the electronic configuration which are completely half filled or completely filled, they have symmetry, and we know that symmetry causes stability. Then we have the exchange energy. The stabilizing effect arises whenever two or more electrons with the same spin are present in the degenerate orbitals of the subshell. These electrons tend to exchange their position, and the energy released due to this exchange is called the exchange energy. You can see, my dear students, that we have 5 electrons filled into these d orbitals. This first electron exchange its position with the second, first with the third, first with the fourth, first with the 5. So this first electron makes 4 exchange, then the second electron makes second with 3, second to third, second to fourth, second to fifth. So third electron makes 3 exchange, then second electron makes 3 exchange, then third electron makes 2 exchange, and fourth electron makes 1 exchange. So when the electron exchange their position, due to this exchange of their position, some energy is released, and this released energy is known as the exchange energy. In the figure, possible exchange for d5 configuration has been shown. The number of exchange that takes place is maximum when the subshell is either half filled or completely filled. So when these exchanges are more, the more are the exchanges, more the energy is released, and that is why more is the stability. So here you can see that if you have D2 or D1 or D3, you will find less exchanges, but in case of the D5, you have more exchanges, and that is why the D5 is considered as a more stable, and that is why whenever we have D4, instead of D4, we get D5 electronic configuration. Sorry, dear students. At the same time, whenever we have D9 instead of D9, we always get D10 electronic configuration. As a result of exchange energy is maximum, so stability is maximum. Exchange energy is the basis for the Hund rule. Please remember, my dear students, that exchange on the base of the exchange energy, Hund rule is being formulated, which says that first all the electrons are filled with the same spin, and all the orbitals which are degenerate, they are occupied singly, and then the pairing starts. So this is what it happens because exchange energy helps in this particular direction, and due to exchange energy, all the electrons are filled with the same spin so that they can exchange their position and they can have more stability. Exchange energy is the basis of the Hund rule that electrons which enter into the degenerate orbital maximum same spin as far as possible. The extra stability of half filled and completely filled subshell is also due to the relatively small shielding. You know, if the electrons are filled with the same spin, they provide the small shielding. At the same time, smaller Coulombic repulsion energy when the electrons are filled with the same spin, they are filled into the separate orbital, and that is why they will have less Coulombic repulsion if they are filled in the same orbital. They are more near to each other and they feel more Coulombic repulsion. And then we have the large exchange energy that we have studied about the the uh, the exchange energy, and this is how we can understand that completely filled and completely half filled electronic configuration is considered to be the more stable electronic configuration. Now let us understand the definition of core electron. The electron in the completely filled shell are known as the core electrons. Example, in carbon Z is equal to 6, we have 1s2, 2s2, 2p6 but 2p2, but in place of 1s2 we write helium. So carbon electronic configuration is helium 2s2 2p2, and this helium is known as the core electrons, whereas 2s2 and 2p2 they are known as the valence shell electrons. Same way, my dear students, for potassium we can write Z is equal to 19. So 19 electrons are filled in the order of 1s2, 2s2, 2p6, 3s2, 3p6 for S1, but for 1s2, 2s2, 2p6, 3s2, 3p6, they are known as the core electron, and that is why we represent them with the inert gas argon, and this electronic configuration is known as the core electronic configuration, whereas for S1 is known as the valence electronic configuration, or for S1 electron is known as the valence electron. So let us understand the definition of valence electron. The electrons that are added to the electronic subshell with highest principal quantum number are known as the valence electron. For example, in carbon 2s2, 2p2 are known as the valence electron. In potassium, 4s1 is known as the valence electron. That is what I have already discussed. Now, what is the utility of knowing electronic configuration? Why should we study electronic configuration? What is the need of studying electronic configuration? So modern approach to the chemistry, in fact, depends almost entirely on the electronic distribution to understand and explain chemical behavior. My dear students, whenever we will study the properties of elements in future, we will study about electronic configuration, and almost everything we will study based on the electronic configuration, so you will understand it better, but it is very important concept. Answers to the following questions can be easily given by understanding the electronic configuration. These questions are: why two or more atoms combine to form molecule? why some elements are metal, why some the other elements are non-metal, why halogens are reactive, and why helium, neon, argon, krypton, xenon, radon, they are the noble gases or inert gases, and they are almost non-reactive. To write the electronic configuration of any element, we should know few things. Now I am teaching you, my dear students, please pay proper attention and learn how to write the electronic configuration of any element if you are given the atomic number. So let us look at this atomic number or number of electron present. You must know. There are few things which you must know if you want to write the electronic configuration, and the first one is you should know about the atomic number, because knowing the atomic number you come to know about the what is the number of electrons that can be filled. Now we will study about the order. This order you must learn it by now at any cost. So this order must be known to you. It is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5d, 6d, 7p, 8s. Then of you should know the electronic configuration of the inert gases. So this electronic configuration for the inert gases, you must know it well. So you need to learn this electronic configuration well. You need to learn even their atomic number if needed. So please learn their atomic number also, and please learn this table well. So helium atomic number is 2, it is 1s2. Neon atomic number 10, it is helium 2s2 2p6. Argon atomic number 18, it is neon 3s2 3p6. Krypton, it is 36, it is argon 4s2 3d10 4p6. Xenon atomic number 54, it is krypton 5s2 4d10 5p6. Radon, it is atomic number 86, it is xenon 6s2 4f14 5d10 6p6. This electronic configuration of the inert gases are going to be your guiding light for writing any electronic configuration of any element. At the same time, you should know the electronic configurations of some exceptional elements. Now, this electronic configuration, you must learn them by heart. So, let us look at the various exceptional element where they have the exceptional electronic configuration. You can understand it, or let us start it. We have Z is equal to 24, which is chromium. The electronic configuration is argon 3d5 for S1. Here 3d5 goes, actually it should be 3d4, but one electron from 4s goes to the 3d, and that is why we have argon, instead of argon 3d4 for S1, it is argon 3d5 for S, argon 3d4 for S2, it is argon 3d5 for S1. This is what it happens because of the more stable 3d5 electronic configuration. Same way in zinc, atomic number is 29, so it should be argon 3d9 for S2, but instead of argon 3d9 for S2, it turns into more stable argon 3d10 for S1, and the electron from 4s goes to the 3d. Same way, if you look at the niobium, Z is equal to 41, it is krypton for, it should be krypton 43 5s2, but instead of that, it goes krypton 44 5s1, because as compared to 43, 44 will have more exchange energy, and that is why it turned out to be krypton 44 5s1. Same way in the molybdenum, you can see their atomic number is 42. Krypton, it should be krypton 44 5s2, but instead of 44 it turns into 45, and the electronic configuration is molybdenum Z is equal to 42, krypton 45 5s1, because the electron from 5s goes to 40 to make it more stable 45. Same way in the ruthenium, Z is equal to 44, you can see that it should be the electronic configuration of krypton 46 5s2, but instead of 46 it turns into 47, and the electronic configuration of ruthenium is krypton 47 5s1. Same way in the electronic configuration of rhodium, where the atomic number is 45, it should be krypton 47 5s2, but instead of krypton 47 it turns out to be krypton 48 and 5s1. Same way in the palladium, which is having the atomic number 46, it should be krypton 48 5s2, but it goes like krypton 40 10 5s0. So both the electrons from 5s orbital go to the 4d orbital, and this is how the more stable electronic configuration can be done. Same way we have more examples to learn. In silver, where the atomic number is 47, the electronic configuration should be krypton 49 5s2, but instead of that it goes krypton 40 10 5s1. And now we'll move to the lanthanum. So in the lanthanum, the electronic configuration, the atomic number is Z is equal to 57. So the electronic configuration should be xenon 4f1 5d0 6s2, but instead of electron goes to the 4f, it goes to the 5d, and the real electronic configuration for lanthanum is xenon 5d1 6s2. Same way, if we look at the cerium, the electronic configuration should be xenon 4f2 5d0 and 6s2. Instead of that, it goes, see, electron instead of going into the 4f2, the electron goes into the 5d orbital, and the electronic configuration is xenon 4f1 5d1 6s2. In gadolinium, the electronic configuration, uh, in gadolinium, you can see on your screen, my dear students, that in gadolinium, the electronic configuration should be xenon 4f8 5d10 6s2. Instead of that, the electron become 4f instead of 4f8, 4f7, which is completely half filled, and that is why the electron from 4f goes to the 5d, and the electronic configuration become gadolinium xenon 4f7 5d1 6s2. Same way in the platinum, the electronic configuration should be 4f14 5d8 6s2, but instead of 5d8, the electronic configuration become 5d9, and one electron from 4s goes to the 5d, and that is why the electronic configuration for Z is equal to 178 platinum is xenon 4f14 5d9 6s1. Same way for the gold aurum, Z is equal to 79, the electronic configuration should be xenon 4f14 49 6s2, but instead of 49, instead of 5d9, 5d10 is more stable, and that is why the electron from 6s goes to the 5d, and the real electronic configuration for gold is aurum xenon 4f14 5d10 6s1. Same way, my dear students, we can understand the uh, uh, example of uranium, where the atomic number is 92. The electronic configuration should be radon 7s2 4f4, but instead of that, the electron goes into the 60 orbital, and the real electronic configuration uh, is radon 7s2 5s3 6d1. Same way, my dear students, you can see, like, there are some more examples which I have written on some other pages, where you can see about the actinium, thorium, uh, actinium and thorium, then uranium and neptunium and plutonium even have this kind of special electronic configuration, and you must know all this electronic configuration. Now we are going to do an exercise, and we will study how can we write the electronic configuration of an element with with these various atomic numbers. So let us start and studying how to write the electronic configuration, but these are the must things that you must know. Now we will start with the Z is equal to 7. Z is equal to 7 falls between the helium and neon, because helium has got the atomic number 2 and neon has got the atomic number 10. So Z is between helium and neon. So we can write the, neon is helium 2s2 2p6 and helium Z is equal to 2. So we can start with the Z is equal to 7, which is your nitrogen. And when you have Z is equal to 7, we can start with the previous inert gas. So helium, then the electronic configuration of neon is 2s2 2p6. That means 2s and 2p orbital are going to be filled. Now for nitrogen, Z is equal to 7, if we write helium, then total 7 electron. Out of these 7 electron, 2 electrons have gone for helium, so 5 electrons are left. In s orbital maximum, we can fill 2 electrons.